Right, we're going to start section 1, exploring data, and let's start by looking at the types of data. The types of data are two. There's categorical and numerical. With categorical, we look at things such as pain level, eye color, whereas with numerical, it's things like number of dice rolls or height, where a number is associated. Now with numerical, there's a further two types of numerical data. You have continuous and discrete. With continuous data, there's an infinite number of possible outcomes. So with height, it the level of accuracy can go on indefinitely. For example, think about how a plant grows. It doesn't grow in fixed increments. It grows very gradually, and it's continuous. The data is spread. Whereas with discrete, it goes up in fixed values. Similarly to shoe size, for example, you might have 6, 6.5, 7, 7.5. Whereas with feet growth, it's not discrete; it's continuous. It's not like you're a size 6.5 on your 12th birthday, and when you're 13, you suddenly go up to 7. Your feet grows gradually. Also, marks on the test are discrete, so you go from 90 to 90.5 to 91, 91.5, for example. Again, it goes up in fixed steps, or the number of coin tosses. Right, let's look at an example here. Here's some data examples from A to I, and what I'd like to do is pause the video and label them as categorical, numerical, and if they're numerical, decide whether it's discrete, continuous. Okay, I'm going to go over this using color code. So categorical, I'm going to call yellow, and categorical, where there's no numbers used, are simply A and F. Everything else is clearly numerical. Now with discrete data, we've got, so for the remainder, the ones that are not yellow, if I just do discrete as purple, so B would be discrete, number of aces in the hand, because it's fixed. C would be continuous, simply because of the time in seconds. Whereas D, the fraction of coin tosses, will be again discrete, and E, the number of spectators, is discrete. G is again time in seconds, and the measurement of those seconds obviously can go on to a number of decimal places, so therefore it's continuous. H, percentage gained by students, again is discrete. There's only a certain number of marks you can get within that, and so therefore it's discrete. And H, the number of weeds in 1 by 1, again it's a measure of the number of weeds, as there must be a whole number of weeds that you can have. So therefore C is numerical, but it's continuous, and G is numerical, but it's continuous as well. Right, let's look at some discrete data which can be grouped. One of the things we can use is a stem and leaf diagram. And one of the advantages of a stem and leaf diagram is there's a number of advantages. One of them is that it also gives us an indication of the way the data is actually spread. So here we've got, for example, the data set of heights of a group of 20 A-level students, and they've used a stem of 16, 17, 18, 19. So here's your stem, and these parts here are your leaf. Now there's a bit of a problem with this stem and leaf diagram, and the problem is that the leaves are not in numerical order, so it doesn't really help when we need to do calculations. In order to put them in order, so when you're collecting data, you can firstly maybe put it in this form, but then you do have to put it in numerical order as so. And we can see n equals 20, there's 20 items altogether, And the most important thing here is a key, and this key tells us what the data means. So 16 slash 5 could mean 165. It could mean 165,000. It could mean 16.5. So they're obviously when you draw a key, you need to write down what it means, and so 17 slash 3 means 1.73. Let's look at an example. Here's a stem and leaf diagram, n equals 20, and we've got to calculate the median, the mode, and the mid-range. Right, the first thing is median, and just a little note on median. See, I've got 5 numbers. Let's say 3, 4, 7, 9, and I don't know, 11. So I've got 5 items, so n equals 5. Now, the way to calculate the median is to do n plus 1 divided by 2. And so with 5, I've got 5 plus 1 is 6, 6 divided by 2 is 3, and therefore my third value is going to be my median. So I'll write down median is the middle number when it's in numerical order, and the median is 7. But say now we add a number. So say I've got, let me just get rid of that, 7. Okay, and say we now add a number to this. Let's add 12. Now when I do n plus 1 over 2, here n equals 6. 6 plus 1 is 7. 7 divided by 2, I get 3.5. That means my middle value isn't a single value, it's actually 2. It's the third value here and the next value after that. So what I'm going to do is, when I get a decimal, is add the third and the fourth value, because I've got 3.5. So I'm going to do 7 plus 9 divided by 2, which gives us 16 over 2, which is 8. So the median now equals 8. So in terms of our data over here, we need to count, we always got 20. 20 plus 1 is 21 divided by 2 gives us 10.5, and so therefore we'll take the average of we're looking for the 10th plus the 11th term divided by 2. So if we count numerically, beginning from the lowest, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so therefore the 10th value, let me just carry this over, is, so the 10th value is 1.73, the 11th value is 1.77, add them together and divide them by 2, and that gives me 1.75, which is my median. Let's write down, here's a median. Right, mode is the one that occurs most frequently, and we can see that 1.82 occurs 3 times. So mode is one for the highest frequency, and you get 1.82. Finally, the mid-range is defined as the highest plus the lowest divided by 2. So let me write that down. Mid-range equals the highest plus lowest divided by 2. And so we've got 1.65 plus 1.90 divided by 2, and this gives me 1.775. So that's my mid-range. Right, there is one more average that we can calculate, and it's the mean. So if I've got a data set, say I've got a data set of 1, 2, 3, 4, 5, then my mean is just going to be the sum of all the x values divided by the number of items I've got. So therefore it's going to be 1 plus 2 plus 3 plus 4 plus 5 divided by 5 items. And that gives me 15 divided by 5, which is 3. So there's my mean. Now it's probably worth understanding the comparison of the averages. The mean, I'll just read this out, includes all the data in the average, and so takes into account all the numerical values of the data. So if you have an exceptionally large or really small item, which might even be a mistake, for example, then such an item is called an outlier. It's 2 standard deviations outside away from the mean. And so if you have an outlier, then that affects your values. And so because the mean, you sum all the values divided by n, any such values which might be really big or really small affect it. The median is less sensitive to high and low values, i.e. outliers, as it is simply the middle value in order of size. And so if the numerical values of each of the items of data are relevant to the average, then the mean is a better measure. If not, use the median. Okay, so obviously in the case of outliers, the advantage of the median is not affected by such values. The mode picks up the most common data set, and this is only significant if you've got relatively high frequencies involved. It takes into no account at all of the numerical values of the data. So when you have a lot of frequencies involved, then obviously the mode is really useful. And the mid-range is essentially calculated solely on the highest and lowest items, and this is easy to calculate, but assumes that the data is symmetrical. So if it is symmetrical if it is to provide a suitable measure of average. So if it's not symmetrical, then the mid-range wouldn't be a suitable means of calculating an average.